Okay, so in the last video I talked about binary versus decimal, and I gave a sort of brief overview of that. And I thought I would follow up on that with a little bit more about the binary counting system, in particular show you how to count in binary and how to add in binary, to sort of get a better feel for how that works. So if we look at counting as it normally works, we have 1, 2, 3, 4, 5, 6, and so on, 9, 10, 11, 12, 13. That's far enough. So here's how counting works in the regular decimal system that we're all familiar with. Of course, we have our words for these, and the key point is right here. We get to 9, and then instead of writing some brand new symbol for 10, we write 10 by taking advantage of place value. We write a 1 and a 0 because the 1 captures that we're at 10, and then we're just at 10, nothing beyond 10. And then a 1 and a 1 is 10 plus 1, and 10 plus 2, and 10 plus 3, and so on. And counting in binary, of course, works exactly the same way, except that we have to stop using new symbols, not as soon as we get to 10, but as soon as we get to 2. So we start with 1, but then we're already out of symbols. Our symbols were 0 and 1. So we start with 1, and then for 2, we're already using place value to represent 2. So this is what 2 looks like in binary. 1, 2, and 0 ones. And then 3 looks like this. And then when I get to 4, I increment the 1's column again, but it sort of spills over, and it gives me an increment to the 2's column, which is also out of space, so that spills over and increments the 4's column. So this looks like this. 1, 4, 0, 2's, and 0, 1. So counting upwards in binary looks like this. Right? Once again, I've reached sort of 111, which is the equivalent of like 999 in a decimal system, and I go up by 1 more, and the 1's all flush down to 0s, and I get 1 higher digit out here representing the 8's column. And then 9 is an 8 and a 1, and 10 is an 8 and a 2, and 11 is an 8 and a 2 and a 1, and 12 is an 8 and a 4, and 13 is an 8 and a 4 and a 1, and so on. So this is how counting works in binary. And just to really drive the point home, let's do counting in ternary. Ternary is just like binary, except it's a base 3 system. So we have a 1's column, a 3's column, a 9's column, a 27's column. So counting in ternary looks like 1, 2. I still have my own. 2 has its own symbol, but 3 doesn't have its own symbol. 3 is represented like this: 1, 3, and no 1's. And then 4, 1, 3, and 1, 1. And 5, 1, 3, and 2 1's. And 6, that's 2 3's. And 7, and 8, right? 8 is 2 3's and 2 1's. And now 9 bumps me up to the next column, because 2 2, much like 1 1 or 9 9 9, is maxed out, and I have to use the next column to get a higher number. 9 looks like this. Right? 1 9, no 3's, 1 1, that's 10. 1 9, no 3's, 2 1's, that's 11. 1 9, 1 3, no 1's, that's 12. 1 9, 1 3, 1 1, that's 13, and going on from there. So this is counting in decimal, in binary, and in ternary. And closely related to counting is the idea of adding. So in the little bit of space that's left here, I'm going to talk about addition. So let me write down 2 binary numbers. So here's 1, 1, 0, 1, 1, 0, 1. This is the one, by the way, that I wrote down in the previous video, and it was equal to 45. And let me write down a different binary number. Let's say 1, 1, 0, 1, 0, 0. What number is this? Well, this is the 1's, the 2's, the 4's, the 8's, the 16's, the 32's. So to figure out this number, I can sort of do it on the side down here. It's going to be 32 plus 16 plus no 8's plus 4. So it's going to be 52. hope I got that right. So this number is 52. In brackets, I'm writing it in decimal. And if I want to add these up, I can do addition in just exactly the same way that addition works for decimal numbers. I can do it column by column, and just when a column overflows, I need to carry it over to the next column. So 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1, well, that's 2, but I can't write 2 here. 2 is a 0 with a carry the 1. 1 and 1 is 2 again, so that's a 0, carry the 1. 1 and 1 is 2 again, so that's a 0, carry the 1. 1 and 1 and 1 is 3. 3 is a 1 and a 1, so that's a 1, carry the 1, which is 1. And what number did I get? Well, a little bit of space down here to translate this number. This is, again, the 1s, the 2s, the 4s, the 8s, the 16s, the 32s, the 64s. So I got 64 plus 32 plus 1, which is 96, 97. And indeed, 45 plus 52 is 97. This is just a different way of adding those two numbers up. Instead of using the decimal representation, which of course is faster because I have more symbols, I'm using a binary representation, which is longer and slower, but the only additions I ever needed to make was 0 plus 0, 1 plus 0, 1 plus 1, and in this one case, 1 plus 1 plus 1. So it takes longer, but all of the individual computations are way simpler. And that gives a sense of why binary is useful in the world of computer programming and building computers in the first place. Because computers are good at doing simple things a lot. And binary takes a problem which is short but requires some addition skills and transforms it into a problem which is longer but requires much lower degree of addition skills.